Hello to all my viewers. This is Dr. Dhaval Maheta, and today we will understand how to do reliability and validity testing in structural equation modeling. There are 6 stages of structural equation modeling. In stage 1, we define the individual constructs. Stage 2, we develop and specify the measurement model. In stage 3, we design a study to produce the empirical result. And in stage 4, we assess the measurement model validity. In this stage, we test the reliability and validity of the measurement model. Once it is established, this measurement model is converted into the structural model, which you can see on the screen. Stage 5, we specify the structural model, and stage 6, we assess the structural model validity. The first thing which we do in the measurement model is testing its reliability. So, reliability is synonymous with the consistency. There is a degree to which an assessment tool produces stable and consistent result. It is a degree to which test scores of an individual test taker or a group of test takers are consistent over repeated application. Let's try to understand this concept with a very small example. Can we repeat the same team in next match? So the example which I have taken here is of the football team. If I can repeat the same team in the next match, then I can say that the team is reliable. So the reliability is, are we getting the same result using same instrument every time? If yes, then the instrument is reliable. When we repeat the survey, will it give me the same results? Is my instrument reliable? So if the same instrument is repeated, if it gives me the same result, then it is reliable. Then comes the factor loading. In structural equation modeling, factor loading represents the strength and direction of the relationship between the observed indicators and their corresponding latent variables. So, corresponding latent variables, also known as factors or construct. The all square ones are indicators, and the oval ones, A, B, and C, they are factors or construct. So, it talks about the relationship between the indicators and the constructs. A factor loading is similar to a standardized regression coefficient and can be interpreted as the amount of variance in the observed variable that can be explained by the latent variable. Factor loadings ranges from -1 to +1, where positive value indicate a positive relationship and a negative values indicate a negative relationship. The magnitude of the factor loadings indicate the strength of the relationship, with the larger absolute values indicating a strong relationship between the observed indicator and the latent variable. Let's try to understand the average variance extracted concept here. Loyalty is captured with the help of 4 statements: S1, S2, S3, and S4. The performance of the entire construct depends on the performance of the statement S1, S2, S3, and S4. Say for example, if the factor loading of S1 is 0.708, and if I take the square of it, the variance explained by S1 is 50%. This means that S1 is able to explain variation in loyalty construct by 50%. Now, if I take the average variance, if I take the variance extracted of S1, S2, S3, S4, and if I take this, if I take the average of it, so variance extracted of S1, S2, S3, S4 divided by 4, I will get the average variance extracted of for the construct. The threshold limit is this value should be more than 50%. Validity refers to the degree to which an instrument accurately measures what it intends to measure. Construct validity refers to degree to which a measure actually assesses the theoretical construct. Construct validity can be established through convergent validity and discriminant validity. Let's understand the convergent validity. It is absolutely necessary to establish convergent and discriminant validity as well as reliability when we are doing confirmatory factor analysis. Convergent validity in SAM is the extent to which multiple measures or the indicators of the same construct demonstrate agreement and consistency among them. It is evaluated through factor loading, AVE, average variance extracted, and composite reliability to ensure that the indicators are effectively measuring the underlying construct and providing reliable and valid data for the SAM model. In SAM, factor loading should be statistically significant and ideally above a predetermined threshold, that is 0.5 or 0.7. to demonstrate the convergent validity. Convergent validity is used to check the unidimensionality of the multiple items construct and will help in eliminating any unreliable indicators. Composite reliability and the average variance extracted explains the degree that a latent is explained by its observed variable. Average variance extracted assesses the amount of variance captured by the indicators relative to the measurement error, and the values above zero point 0.5 are generally considered acceptable. The composite reliability measures the internal consistency or the reliability of the indicators, and values above zero point 0.7 are typically desired. The next is discriminant validity. The divergent validity. Divergent validity in SEM refers to the extent to which measures of different constructs are not strongly related to each other. It is evaluated by comparing the correlations between the indicators of the same construct to the correlation between indicators of different constructs. The most common approach is to calculate the average squared variance and maximum SAD variance, or the square root of the average SAD variance between the constructs. ASV or SRV is the amount of SAD variance between two constructs after accounting for the measurement error. Lower values of ASV/SRV indicate greater divergent validity, as it implies that the constructs are capturing unique variance beyond the measurement error. If the correlation between two variables is 0.8, their shared variance will be 0.64. Discriminant validity can only be calculated in first order. Now let's try to understand this divergent validity. S1, S2, S3, S4 are the indicators for the loyalty. T1, T2, T3, T4 are the indicators for the satisfaction. We require a strong correlation among the indicators of the same construct. That is S1, S2, S3, S4. This would be strongly correlated. But we require low correlation among the indicators of the different construct. We don't require a high correlation among T1 to T4 and S1 to S4. You can see here, we require low correlation here, so that there is a very less overlapping among the constructs. If this is established, then we will say that the divergent validity is established. High correlation among statements of the same construct is desirable. Here, high correlation among statements of different construct is not desirable. If it happens, then that is known as a cross-loadings. We require high correlation here, and we require very less correlation here. How to report CFA results? First, we do the validity testing. In that, the construct validity is tested with the help of convergent validity and discriminant validity. The thresholds are composite reliability should be greater than 0.7, AVE should be more than 0.5, CR should be greater than AVE. For discriminant validity, AVE should be greater than MSV, AVE should be greater than ASV. MSV is maximum shared variance. Model fit indices, these are for the structural equation modeling. This we will see later on. Now let's try to understand that a loyalty is a construct which is captured with the help of statements S1, S2, S3 and S4. These are all the error terms. The factor loading is beta. The value which we had discussed is 0.708. If I take the square of it, I will get the explained variance. That is the amount of variance explained by S1 on loyalty. If I take the difference of this, I will get lambda, that is unexplained variance, that is an error term, E1. So what is the average variance extracted? Sigma beta squared. That is the explained variance by S1, S2, S3, S4 is a AV. What is the composite reliability? Sigma beta square. I will take beta from here, not this beta square. I'll take this beta. Sigma beta square upon sigma beta square plus lambda, unexplained variance. So what is lambda? It is again 1 minus beta square. So that is the composite reliability. Variance extracted is the square of standardized factor loadings. So if I take the square of 0.65, I'll get 0.43, which we have seen in the earlier slide also. The relationship of statements with a construct is known as average variance extracted. 0.65 square, 0.56 square, 0.57 square divided by 3. So it will give me average variance extracted. The relationship among statement is known as the composite reliability. So if I take the amount of variance explained, that is 0.65, 0.56, 0.57, and then their error terms. If you recall this slide, and their error terms, unexplained component, then it will give me the composite reliability of A. The relationship of one construct with another construct is known as average shared variance. So the maximum shared variance is, there are two arrows going inside A. One is 0.6 and another is 0.48. You have to take the bigger one. So if you take the square of this, it is 0.36 maximum shared variance. Average shared variance is 0.60 square plus 0.48 square divided by 2 is average shared variance. So the standardized factor loadings, if I take the square of it, I'll get variance extracted. So that is used, that measure is used for average variance extracted. If I take the difference of 1 minus, if I take difference 1 minus variance extracted, it will give me the measured error that is used for composite reliability. Standardized factor loading should be more than 0.708. These are all thresholds. Variance explained is square of standardized factor loadings and it should be more than 50%. Reliability, that is a composite reliability, should be more than 0.7. For establishing convergent validity, the composite reliability should be more than AVE, average variance extracted. Average variance extracted should be more than 0.5. So average shared variance, for establishing discriminant validity, maximum shared variance should be less than average variance extracted, and average shared variance should be less than average variance extracted. It is very simple that why we have to satisfy this equation. Let's go back. What we want is that this figure, the figure of AVE, should be more than this figure. That is the average shared variance and maximum shared variance. If this figure exceeds, it means that there is a possibility that we are having multicollinearity among these two constructs, and therefore we will have to go for higher order models. So it is necessary that AVE, the average variance extracted, should be greater than average shared variance and maximum shared variance. Now let's see how we can do the reliability and validity testing in AMOS. So for this, I'll activate AMOS. I'll bring the data file. Click OK. You should always keep these two tabs open. This tab shows the list of variables in the data set. This tab shows list of variables in your model. So first we have to construct the measurement model. So let us pick up from here. 1, 2, 3, 4. There are 4 indicators for the organizational commitment: OC1, OC2, OC3, OC4. Automatically, it will set a metric 1 for one of the factor loadings. It will do it automatically. In case, if it is necessary to delete any one of the factor loadings, then the model will not run. So in that scenario, you will have to keep 1 on any other factor loading. Now I want to rotate this. So I'll select here and I'll do the rotation. The next thing which I want to do is I want to make another 4 constructs. So select all, preserve symmetries, take the truck from here. So symmetries are not maintained. Let me do the selection again. 1. Now I want to make another 4 constructs. So I will activate the photocopier machine. 2, 3, 4, and 5. Can I decrease the size? Let me check. So I'll minimize it. Fine. And I'll click on this, resize the path diagram to fit on the page. Done. Now again select all and bring it in center. Now I have to name them. So I'll double click on this. So this is a construct. The name is organizational commitment. Then I will click here. This is a construct. The name is job satisfaction. Please don't keep any space here. Job satisfaction. Then click here. It is environmental perception. Then click here. Co-workers, the behavior of the co-workers. Click here. Staying intentions of an employee. Close this. The indicators for the organizational commitment are OC1, OC2, OC3, OC4. 1, 2, 3, and 4. Double click on it. OC1. Make sure that the alphabets tally because it is very case sensitive. If you write it in small, then it will run an error. Again, click here. OC2. Click here. OC3. OC4. Now the indicators of the job satisfaction are JS1. You can see here JS1, JS2, JS3, and JS4. JS1, JS2, JS3, and JS4. Environmental perception indicators are EP1, EP2, EP3, EP4. The co-workers indicators are AC1 to AC4, AC1, AC2, AC3, AC4. Probably here there is one mistake. It should be EP4. Sorry, EP4. Let me take AC1 here only. Does not matter. AC1. At AC1, 2, 3, 4. Staying intention. SI1, SI2, so these are indicators for staying intention. Click here. SI3, and this is SI4. Okay, so you can see here the variables which have been taken in the model. Now we will have to co-vary all this construct. So pick up this, select one object at a time. 1, 2, 3, 4, 5. Make sure that they turn blue. Now you can connect them automatically. Go in plugins, draw covariances. Done. Now you want to bring this covariances this side. So there is automatically a resize button will appear. You can see a square button. If it does not appear, you can pick up from here the change the size of the objects. Now what you can do is you can select it and you can bring all covariances this side. Pick up the magic wand from here to make the diagram clean. Now these are all the error terms. It is not possible that any one of the indicator can explain organizational commitment 100%. There will be definitely an error. The another example is that you select a football player. It is impossible that this football player will not commit a mistake. So this is an error. The error terms have been introduced. But we will have to give the name to this error term. How we can give this? Again, go in plugins, name unobserved variables. Done. So each error term will be given the unique names. Now we have to run the model. So click here, analysis property, output, standardized estimates, squared multiple correlations, keep other things as it is and run it. It will ask the location where you want to save this file. So write down HBAT demo save. You got the output. Now you click here. Go in estimates. So the regression weights are ready and standardized regression weights are ready. You can test the model fit from here also. Now there are two ways in which the reliability and validity of this model can be tested. We'll see the first method. The first is using the Excel sheet. Now this Excel sheet, you will get it from this website, StatWiki Designation, developed by James Gaskin. You click on Excel Stats tool and it is a free stats tool given by Professor James Gaskin. You will be able to download it very easily. Once this is done, you will go in Validity Master. It requires the correlation and it requires the standardized regression weights. So again, go in the output window and go in estimates and go in correlations. So you can see here the correlations are there. What you will do is right click on it and copy. Again, go in the Excel sheet and you can see here this cell. Paste correlations table in A2. Press Ctrl V. Done. The next thing which you have to do is you require the standardized regression weights. So again, you will go back and activate the standardized regression weights, copy, and again you will paste it here. Make sure you paste it in the orange cell, that is F2, Ctrl V. Now to run this Excel sheet, there are some caveats. The first is your latent variables name do not end in numbers. That is F1, factor F12. It is okay to have observed variables named whatever you want. So that's the same thing which we have done. Your error residual names do not end with the numbers. Your variables names are not any of the following. That is, you are not using the terms like AV, max, CR, MSV. You have more than 2 latent variables and you have no Haywood cases. This we will see later on. If all these 5 conditions are satisfied, click on this red tab. Quite good. You have got the results. So you can see here, it has given us the statement, no validity concerns. Now I have copied this Excel sheet in my presentation to make things simple. I also included the model which we got from here. Let me show you the model, just a minute. This model. To get the figures on this, I'll just press this up arrow. So I've got these figures and I've copied this on my Excel sheet. Okay, let's try to understand. First check, is reliability established of each and every construct? So we'll check the composite reliability. This value should be more than 0.7. If it is there, quite good. Next is convergent validity. The composite ratio should be greater than AV. Is it greater than? Yes. Is AV greater than 0.5 of all the constructs? Yes. It means that the convergent validity is established. The next task is to see that the maximum shared variance should be less than AV. I already explained this why we want that the maximum shared variance among these two constructs should be less than the average variance extracted by the single construct. So this figure is less than AV, MSV is less than AV, and therefore we can say that the discriminant validity has been achieved. The next is the Forner-Larkin criterion. Here, how I got this figure 0.824, quite interesting. If you take the square root of 0.678, take the square root of 0.7678, you will get 0.824. Take the square root of organizational commitment, take the square root of AVE of organizational commitment, you will get 0.751. 0.519, you will get 0.720, 0.602, 0.776, and 0.670, you will get 0.818. Now, what are these figures? 0.307, 0.025, 0.253. What are these figures? These are the correlations. Let's see, organizational commitment with co-workers. The figure is 0.307. Organizational commitment with co-workers, the arrow is this one. See, it is 0.31. Now, let's check the co-worker with job satisfaction. Co-worker with job satisfaction. The arrow is this one. And it is 0.02. Yes. Co-workers with environmental perception. Co-workers with environmental perception, the figure is 0.25. Here, see 0.25. Co-workers with staying intention, 0.308. Co-workers with staying intention, 0.31. So, the correlation of all other constructs are calculated. Now, how to interpret? The interpretation is diagonally. Diagonally, this value should be maximum in corresponding columns and rows. See, 0.824 is a maximum value in the corresponding column. Here, it is maximum. 0.75 should be maximum in corresponding column. Here, that is 0.751 is greater than 1, 2, and 3. And it should also be greater than the corresponding row, that is 0.307. 0.720 it should be greater than corresponding columns 0.229, 0.214, and 0.720 should be also greater than corresponding rows. This is basically the Forner-Larkin criterion. If this is there, if this condition satisfies, then we will say that the discriminant validity has been achieved. So the first method is CR should be greater than 0.7, AVE greater than 0.5, CR greater than AVE, AVE greater than MSV, AVE greater than ASV. This has also been explained to you. Now we are also having the validity master developed by Professor James Gaskin. You can see here this validity master. There is validity and reliability test. But how will I get this? Let's try to understand. For this, again you will go on this page and you will click on the plugin folder. Then depending upon your version of AMOS, my version is 24. So I'll click on it and I'll download this master validity folder. So let's see, I'll download it. Now I'll go in the download folder. It will give you this warning. No need to worry. Press keep. Press keep. And again go in downloads. Now this validity master, when you will right click on it and when you will see its properties, it will be, you will have to unblock it. Then only you will be able to use it. You will click here and unblock it. Then after unblocking it, you will have to place this master validity folder. So click on it, apply. And you will have to copy this master validity folder into the path. So you go in C, users, possibly here your name will be there or it will be admin. So admin, then you will go in app data, then you will go in local then you will go in MS development, then you will go in MS 24, then you will go in the plugins and paste this .dll file here, master validity .dll file here. Once you have pasted this option will get activated. The validity and reliability test. This option will get activated. Now simply you have to just run it and you will get the output white code. So whatever we have done it manually using the Excel, it has given me here. So just check the figures. 0.751, 0.720 are the same figures. Yeah, it's same figure, 0.75, 0.720. The chronology may be different, but things are quite good in the same format. Here also, we have got the remarks. There are no validity concerns, quite good. HTMT, that is a heterotrade monotrade ratio. We can achieve HTMT when these figures are less than 0.85. HTMT is also used for establishing the discriminant validity. So there are no warnings for the HTMT analysis, and this is also quite good. The last thing which you have to remember is that when we are having a high correlation among two constructs, we should go for higher order models. For more videos on SPSS AMOS, kindly refer my playlist in which I already uploaded many videos on it. Please don't forget to subscribe my channel and press the like button. You can also follow me on LinkedIn and Twitter.